the last time we stopped in 3.3 where we talk about the momentum equations. So we continue with 3.4, which is the energy equations. Firstly, we start with 3.4.1, the energy conservations. So basically for this, the energy conservations for CFD, it applies the first law of thermodynamics, where the time rate of change of energy is equals to the net rate of heat added plus the net rate of work done, where the time rate of change of energy for the moving fluid is equals to this. And actually how it is derived is quite similar to the momentum equation. This is for x, y and z dimensions components. For the net rate of heat added, it is actually the net rate of heat addition to the fluid within the control volume. And meanwhile, the terms on the right is the net rate of work done by surface forces on the fluid. This figure shows the work done by the surface forces on the fluid, and the second shows the heat added to the fluid within the control volumes. So for this case, it only shows the x directions. This is only for one component, one dimensions, which is in x directions. The below equations is how the total or the overall equations of the conservation of energy in three-dimensional. Okay, how it is done. Okay, this only for example, this is only for x dimensions. So we just need to sum all of this work done by the surface onto the fluid, and also add together with the heat added in the control volumes. So basically for this, like for example, for strain xx, so basically this will cancel each other. So basically what you're going to have is only this term. So that's why you have this. Meanwhile, the rate of the change in energy is equals to rho dE over dt xyz. So here we have xyz as well, and then it cancel out. So same goes to this is for y component, this is for z component. Okay, so same goes to the rest. Okay, so you just need to sum all of them. And then you can obtain the equation for the conservation of energy. And then for this, basically the equations that comes from the slide before. And then by applying the Fourier's law of heat conductions, the energy fluxes, where the energy fluxes is this Q. It's represented by Qx, Qy and Qz. They are defined as this, where lambda here represent the thermal conductivity. And then by substituting this all flux into the energy conservation equations, we arrange it to different equations. Basically, the derivation is very long. So even if you look at some books, you need to refer to appendix. So for that, you can just skip it. And then after several derivations and several substitutions and etc., you can get simpler equations, and basically this equation is the one that we use in CFD. So let us consider a special case where the flow is two-dimensional, incompressible, and the continuity equation applies. So it's two-dimensional means that it only has an x and y, so only two dimensions here. There is no z. And incompressible, it means that the density is unchanged. Okay. So with assumptions that the temperature is invariant along the z directions, it is because it is two-dimensional. So whatever variations that happens in the z directions in terms of like pressure, velocity and temperature, you can just assume it constant. And also the thermal conductivity K is constant. Okay, the physical interpretation of this equation, like I mentioned in the previous classes, like all of these terms, it has their own meanings. So like from this equation itself, let's say that from the parameter, from the value, you can already like understand how the physics of fluid or heat transfer actually plays its roles in the flow structure or the temperature field in a flow. So you start with like example of like advections. Like for example, you have like sauna. Imagine that okay, you are sitting at the higher place. So like you know that when in a sauna or in a very hot place, due to the buoyancy effect and due to the density of the gas of air that is hot is lighter than the air that is cold. The upper regions of that room is usually hotter because hot air will goes up. So you feel like okay, it is hot up there, and then you decide to go down, you will feel that it is colder. Okay, just ignore the emoji. Actually, it's quite over. It's not like that cold in sauna. I just want to show that okay, actually it's cold down there. Good. So it is what we call it as advection. The temperature varies with respect to location. Okay, what happened if someone open the sauna door? Okay, you have a cold air outside, and of course due to the difference in density, so the cold air will come into due to the difference in the density. So the air in the sauna and the air outside will change their place. Like the one that is in the sauna will goes out, and the one that cold air, which is more denser, will get into the sauna room. So what you are going to feel is you will feel cold air blowing into the sauna room. This is what we call it as the local accelerations. At that moment, the temperature around you in the sauna immediately drop because the presence of the cold air out from outside. Okay, meanwhile for the diffusion, okay, we use different examples instead of using the sauna. Okay, for diffusions, we use the examples that we've seen before, where we use in the momentum equations, physical interpretations before. We use very similar setup where you have two parallel plates and there is fluid flowing in between the two parallel plates, but this time the plate is heated, so it's hot compared to the temperature of the fluid. The temperature of the fluid is colder for this case. If the velocity of the fluid is very low, it is what we call it as a conduction through the heat diffusion dominating. How the temperature travels in the fluid is similar to what happened in solid. So it's as if like the temperature is conducted into the fluid, where the temperature in the fluid will be saturated very early, very close to the inlet. So that is what happens if the flow is very slow. The heat transfer from the surface to the fluid is not really that good because the fluid will become hot. So that means as the fluid travels further, the heated surface is not going to be cooled down because the difference in temperature between the fluid and the temperature of the surface is no longer different. They're going to be saturated, which is that means that the temperature at the surface and the temperature at the T at the fluid near the wall is similar, so there's no heat transfer occurs. Meanwhile, when the velocity of the fluid is high, it is a local accelerations and advections dominating. So it depends. If the flow is unsteady, it has this local accelerations dominating will take place. Meanwhile, if the flow is steady, it is advections dominating. So what is going to happen is, since the fluid is moving very fast, we keep supplying cold fluid into the domain. So that means that it's going to keep supplying cold fluid. The fluid in the domain will take quite some time to become hot. This is what advections dominating is. Usually, like if we study heat exchanger, one of the parameters that is going to improve the heat transfer efficiency, is the Reynolds number, where it affects the velocity of the fluid. This is one example. We consider a two-dimensional CFD case of the incompressible laminar flow between two stationary parallel plates to illustrate the physical meaning of the energy equations. This is very similar to the one that we discussed in the previous slide. So using CFD and the dimensions of height, h equal to 0.1 and L equals to 1, with air is the working fluid density equals to 1.2 kilograms per meter cubic, a specified uniform temperature of 330 Kelvin at the inlet, and a wall temperature maintained at 300 Kelvin. So discuss the development of the temperature profiles between the inlet and thermal entry length LT for the following cases. So that means that the wall temperature is lower than the temperature at the inlet, where it is 300 Kelvin at the wall, and 330 Kelvin at the inlet. So you see that the surface of the temperature surface is lower than the inlet temperature. So thermal entry length location from the inlet surface in the two-dimensional laminar flow between two stationaries. So that is LT. So usually this LT will determine whether it is diffusion dominating or local accelerations and advections dominating. So you can see for for the fixed inlet velocity 0.01 and thermal conductivity 0.04 and 0.01. So for the first part, we have the same inlet velocity for two cases, but with different thermal conductivities 0.04 and 0.01. And then we have there's another case where a fixed thermal conductivity 0.04 but with different inlet velocities 0.01 and 0.1. So this is what is obtained for the case where the inlet velocity equal to 0.01 and thermal conductivity 0.04. So as we can see that this actually is still developing. So as x equals to 1.5 h, the profile will keeps unchanged, like above this 1.5 h. So that means that LT here, this 1.5 h is the LT, is the thermal entry length. Okay, this is the difference when you have different thermal conductivity. So you have a similar, identical inlet velocity 0.01, but the left one is with the lower thermal conductivity and the right one has a higher, 4 times more the thermal conductivity. So if you can see here, the length of the thermal entry length for the left one is 9h. The thermal entry length for the right one is 1.5h. It takes the left one is longer times to becomes fully developed. So why is only advection terms dominates? Like in the one that we discussed before, it is local and advections dominates. It's only advections, it is because the flow is steady flow. So local accelerations is equal to 0. So it's not going to dominate the flow. So we only have advections and diffusions